Hello and welcome to the second online lecture for Philosophy 470. In this lecture I want to just give you a little bit of background about first order logic and basic definitions of truth and the basic language we'll be working with. Alright, now the language of first order logic consists of a number of different symbols. We have a set of variables, a set of constant symbols, a set of function symbols, a set of predicate symbols, including a special predicate equality. So we always have equality in our language, and then we have our logical symbols, and we use parentheses as grammar to help interpret sentences. Now, the full language of first order logic starts by looking at these first three components, the set of variables, the set of constant symbols, the set of function symbols, to define a set of terms. And what a term is just a way of naming particular objects in your domain. So let's imagine that we have some domain here, some set A, and we want to talk about elements of A. The variables, the constant symbols, and the function symbols are ways of talking about elements of A. And then the predicate symbols are ways of talking about properties of the elements of A. Okay, and the logical symbols are what we use to pull it all together. All right, so formally, a term is constructed as follows. So this notation is a way of saying that a variable x is a term, or a variable c is a term, and if you have n terms, t1, t2, or tau1, tau2, all the way up to tau n, you can construct a new term by applying a function symbol f to that term. So for example, f of x, g of x, f of c, d. This is an example of a term. So it's a term, I'm assuming here the function symbol f is a binary function, so it accepts two arguments. And g looks like also a binary function, so it accepts two arguments. Okay, and the intuition is that a term just simply names objects in your domain. Okay, so terms are built out of these first three symbols. Once we have terms, we can talk about properties of terms. And the property of terms, so we start by defining atomic formulas. So if P is a predicate symbol, it's an n-ary predicate symbol, so it's a relation between n different objects in our domain. P of tau1 up to tau n is going to be an atomic formula. Okay, and this just says the intended interpretation is that the objects named by each one of these terms, tau1 up to tau n, are related according to this predicate P. Now, once we have atomic formulas, we can define our formulas. So formally, a formula, so note the similar notation, is constructed recursively as follows. Atomic formulas are called formulas. And then once we have formulas constructed, phi and psi, for example, we can put a negation in front of it, a conjunction in between two formulas, and we can add quantifiers. I'm assuming that you have seen, you've taken a course on first order logic and propositional logic, and you've seen this type of construction before. The other logical symbols, like disjunction, implication, if and only if, and the existential quantifier, those are not formally part of the language, but we assume they are defined as usual. So for example, phi implies psi, that's just equal by definition to not phi or psi. Well, actually, we only have conjunction in our language, so this really should be not phi and not psi. So phi implies psi is just going to be defined to be, it's not the case that phi is true and psi is false. Okay, so that's our language. To interpret our language, we need to give ourselves a model. Okay, and what a model consists of, so a model A consists of a domain. So this A here is a set, and I is the interpretation function. So it's how you interpret the basic symbols in your language. A substitution tells you how to interpret the variables in your language. So a substitution assigns to every variable the element of the domain that you map it to. All right, so an interpretation just tells you for every constant symbol, for every function symbol, and for every predicate symbol, which element of A or function on A or predicate on A those symbols correspond to. Okay, and now we can see exactly why I say each term is associated with a particular element in the domain. So we write tau of AS, this is the interpretation of the term tau. So you have tau, and I want to interpret it, and the interpretation is going to be some element in A. And the interpretation is defined recursively as follows. So X is just going to be the element that the substitution, so you need to give both a model and a substitution. So X is just the element assigned to it by the substitution. The interpretation of the constant symbol C is just going to be whatever I says C is interpreted as. And to interpret function symbols, you first interpret the function symbol f, and then here this is saying f is applied to n different terms. You have to then recursively interpret each one of the terms. Okay. Now once we have that, we need a few other pieces of notation before we define semantics of our language. If S and S prime are two substitutions, we say that they are equivalent sub x, so S and S prime are equivalent sub x, if they're the same function, so they assign the same values to all variables except a possibly at x. Okay, so the S and S prime are the exact same function. They assign the same elements of the domain to every single variable except x. If S is a substitution, so we have some substitution S, this is just a map from the variables to A, the element A. S of x replaced by A, this is a new substitution. So I have a mistake here. So S of x by A applied to y. That's just going to be the old function applied to y. At all variables except for x, and then it's going to be A when y is equal to x. So we have S of x by replaced with A of y. That's just going to be S of y. But when you apply this to the variable x, you just explicitly say the value, the object assigned to x is going to be A, little a. Okay, so this is the way substitution works on our substitution functions, but we can also do a substitution syntactically. So the idea is that you have some formula phi, and we write phi of x replaced by tau, where tau is a term. This is just going to be the formula phi prime, which looks just like phi, except every single instance of x is replaced by tau. Now, it's not literally every single instance of x, it's only the instances of x that are not bound by a quantifier. So for example, for all x px, this is a formula where x is bound by this quantifier right here. But we might have something like for all y py, let's say, implies px. Here, x is free. X is not bound by this quantifier, even if we put these in parentheses. Okay, so if we try to replace x with, say, the constant c, this is just going to be the same formula because x is bound by this for all quantifier. But here, if we replace x by c, we can do it because x is free. So this will be for all y, py implies pc. Okay, again, I'm assuming you've seen all of this material before. I just wanted to remind you of some of the basic constructions. Here are some examples. So if we have the formula, the atomic formula x equals y, and we replace y with x, so y is the variable and x here, we're thinking of x as a term, this is just going to be the formula x equals x. Okay, so we rewrote this formula, but wherever we see a y, we replace it with an x. And similarly, if we replace now x with y, we're going to get y equals y. But now, if we bound the variable x with this quantifier, and we try to replace x with y, we just get the exact same formula. But here, y is not bound by this quantifier x. And so we get the trivial formula for all x, x equals x. This is the example that I went through earlier. And this is yet another example you can think about this. This says for all x, if it's not the case that everything is equal to x, then it's not the case that everything is equal to x. So here, this for all x bounds this quantifier x. But in this case, this quantifier here is not binding this variable x. So when we replace x with y, we can't replace it here because x is bound by this quantifier, but we can replace it here because x is free. Okay, so this says this formula here will be true if you have more than one object in the domain, but this formula will essentially almost never be true because this says there is something that's not equal to itself. Okay, so you have to be careful when you substitute variables for variables. What happened here is after substituting x for y, x is free. Now both variables in this equation here are now bound. Okay, now this is a phenomena that is quite standard, and you talk about this a lot in Philosophy 370. So see my notes for a discussion, for a more detailed discussion. All right, now we're ready now to define truth in a model. If we have a model and a substitution for A, we interpret formulas. So an arbitrary formula, we interpret that in a model given a substitution S. Oops, there's a mistake here, so this should be AS models phi, is defined by recursion as follows. Well, we say an atomic formula is true if and only if you first interpret each one of these objects. So each one of these terms, you interpret it as a specific object. And then you simply ask, is it the case that this tuple is in the interpretation of P? So the notation this is just alternative notation for saying I of P, where I is the interpretation in the model. We say that two objects are equal if the things that they name are really equal to each other. Strictly speaking, this is a symbol in our language, and this stands for sort of real equality in the structure. A negation is going to be true just in case the formula is not true. Conjunction is true if and only if both conjuncts are true. And now the quantifier, so what intuitively we want to say is that everything in the domain has property psi, just in case. So that's how we interpret this. So the way we do this is we look at all the substitutions that are just like S, except possibly on the value x. So we quantify over all substitution, keeping all the interpretation of the variables fixed, except for possibly x. So for all x psi is true, if you look at all possible substitutions that are just like s except keeping variable x fixed, if you have such a substitution, then psi has to be true there. All right, so this is just a very quick reminder of the basic definition of truth. Again, I'm assuming that you have seen this before in Philosophy 370 or another course. You can consult my notes for more details. The type of structures that we're going to be interested in this course, essentially the whole semester, we're going to study these 4 structures. And I just wanted to put it up here to say how we're denoting it. So N here is a structure. The object or the set of objects are going to be the natural numbers. So 0, 1, 2, 3, the counting numbers, including 0. And then we have these symbols in our language. So we have 0, which is going to be a constant symbol. The successor function, less than, plus, times, and this stands for exponentiation. So taking exponents. And we can look at different substructures of that. So we can restrict the language by restricting to, say, just the constant 0 or the successor function s. We might include the less than relation or maybe plus or times. But in general, these are the structures that we will be studying this semester.